All right, everybody. Welcome to Astro-BS. I'm Samuel Singer, the founder and executive director of Wyoming Stargazing. And I'm here with three of our stargazing leaders, Matt Graham, Ryan DiGregorio, and Dave Martin. And we are going to talk about the recent announcement of the 2020 Nobel Prize being awarded to, in physics, to three prominent astronomers. Roger Penrose, who is being awarded the prize for his work on determining that black holes are in support of the prediction of the general theory of relativity. And then Reinhard Genzel and Andrea Ghez for their work in determining that there's a supermassive black hole in the center of our galaxy. So we're going to start with that, and we'll get into stuff about black holes and special and general relativity, and I think it'll be a hoot. So I'm going to share my screen with you here so you can actually see some pictures of these astronomers. So here's a sketch of Roger Penrose. He's still alive today, and as I mentioned earlier, he was doing a lot of work with Stephen Hawking when Stephen Hawking was still alive on understanding black holes, and their work together help to show that the existence of black holes was in support of Einstein's general theory of relativity. And so this year he'll share the Nobel Prize in Physics with this other astronomer, Reinhard Genzel. Hopefully I'm pronouncing his name correctly, for his discovery in collaboration with Andrea Ghez that there is a supermassive compact object in the center of our galaxy, which we now know is a supermassive black hole that we think are in the center of all big galaxies in the universe. And that's, yeah, a big step in our understanding of how galaxies work. So maybe first we should just talk about what a black hole is. They are pretty strange beasts, and we can kind of create a base from which we're all talking about with these three physicists to start with our understanding. So what about one of those stargazing leaders? Do you guys want to provide a simple definition of a black hole for everybody?
I think a good way to interpret it is just a region of space-time that is so dense and its gravity is so strong that nothing can escape its influence, not even light. And it's basically a curve in space-time, and at the center of it is something called a singularity, where essentially curvature is infinite. And scientists don't really have a great idea of visualizing what a singularity is. It's sort of where physics and time break down. And yeah, so that's why they're these really esoteric entities.
Nice. Thanks, Ryan. And yeah, Ryan did a nice job there. And I'll just add that the big issue in understanding what a black hole is, because it really is a physical object in space. It's one that has an escape velocity greater than the speed of light. So on Earth and on every large, massive object, be it a planet or a moon or a star, there's a certain velocity that you have to travel in order to get out of the gravitational field of that object. We'll talk about gravitational fields in a minute and how that works with space-time that Ryan mentioned. But for now, just know that you have to travel at some velocity to get out of the gravitational field of every massive object. And on Earth, I think it's about 7,000 miles an hour. That's the speed at which you have to travel in order to overcome the pull of gravity, bringing you back down to the surface. So every satellite we've ever launched, every rocket that gets into orbit has to travel at least that velocity, the escape velocity of the Earth. Well, the more massive an object is, and the denser an object is, the stronger its gravitational field. So obviously, to escape the gravitational field of the sun, which is way more massive than the Earth, you'd have to travel much, much faster. Take that to the extreme, to a black hole, and to escape the gravitational pull of a black hole, once you're at a certain proximity from the center of a black hole, this proximity that we call the event horizon, once you pass that point, the escape velocity of a black hole exceeds the speed of light. And from Einstein's theory of special relativity, we know that nothing that has mass can travel at or above the speed of light, and not even light. And so because the escape velocity is greater than the speed of light beyond the event horizon, that's it. Nothing with mass and nothing without mass, light, can escape the gravitational pull of that black hole, which is why they're black, because no radiation can escape beyond that point. So that's what we're talking about when we mean a black hole. Did any of you guys there have anything to add about black holes?
Well, I just had a question. And when you said the escape velocity of a black hole is greater than the speed of light, it sounds like you could come up with a velocity that one would have to travel to escape a black hole of a certain mass. Is there a calculation that can provide you with that?
Yeah, there is. I can't remember what the equation is called right now.
Well, just escape velocity from just any body is like root 2 gm over r.
Yeah.
But then what would you put r as? Would that just be the Schwarzschild radius of it?
It is the Schwarzschild radius, yeah. Yep.
Okay.
Yeah, exactly. Yeah, so Ryan's talking about, I can actually, let's see if I can bring up that equation just to show everybody. Equation of escape velocity. There it is. No, it's not a very good picture of it. There we go. Cool. So yeah, they even got a reference to black holes here. So the escape velocity is the square root of 2 times the gravitational constant, the gravitational universal constant, force of gravity, the mass of the object divided by its radius. And so the radius down there, I'm gonna try to find a better picture of that. So I'm not looking at all those different images moving around. Of course, Pinterest is not going to let us off their website. We can just look at that one there. Divided by the radius. And so in terms of the black hole, it's the Schwarzschild radius that Ryan mentioned, defined by another physicist who came up with where the escape velocity would exceed the speed of light. Is that what you were asking, Ryan?
Yeah, because I remember one of my classes in undergrad, we were talking about the Schwarzschild radius, and that usually if you plugged in the numbers for a black hole, you would get V to equal C. And so like you would have to travel at the speed of, or like just above the speed of light to escape it. But something bothered me with that because I don't think that escaping a black hole just requires just some velocity. I think there's like something else about it where you have to essentially time travel in the wrong direction. You have to like, it would be like violating causality. You wouldn't be able to escape it regardless of how fast you went.
Interesting.
And I don't remember her exact explanation, my professor, but
yeah, I don't remember that either, to be totally honest with you. So what I do know is that there are several paths that light can take just beyond the event horizon where it can escape the gravitational pull of the black hole. It's only once a photon gets at some distance from the event horizon that it will eventually spiral in to the event horizon. I don't remember, it is some ratio of the Schwarzschild radius. I don't remember what ratio, but as long as it's beyond that distance from the event horizon, there can be a path away from the black hole. And the photon won't eventually spiral in past the event horizon. But I don't think any laws of causality are broken. But I do think that if you did skim near the surface of a black hole, skim near the event horizon, you would experience extreme time dilation. And so even if that skimming just took a matter of minutes, or, you know, maybe an hour for you, it would be several years back on Earth. Not only because of how fast you are having to travel to escape the gravitational pull of the black hole, but because of the extreme curvature in space-time, because of the strong gravitational well you would be traveling through. That also affects time dilation. So yeah, the huge speed and the huge warping in space would lead to years passing for an object not traveling that fast and in a weaker gravitational field. There's actually a great kids book about that by Brian Greene, famous physicist. The book is called Icarus at the Edge of Time. So it's the Icarus story, but it's set in the future. And so Icarus is this young kid who's this amazing engineer, and he builds this spacecraft that can do just what we talked about, skim just off the edge of the event horizon. But he forgets to take into account time dilation. So he takes his ship and skims down past the black hole. And when he finishes that route and goes back to where he started, just like a light year away or less, he's like thousands of years in the future. So yeah, pretty wild stuff. Any thoughts come up for you guys about that stuff while we're just chatting about it?
Actually, yeah. So I've discussed the idea of time dilation with people before, and what they seem to struggle with the most is the idea of like biological processes themselves operating at a different speed, essentially.
Got it.
And I've never really been able to explain that in a way that they sort of accept. I don't know. I'm just kind of curious if anybody else might have an explanation to offer.
Well, I remember another one of Brian Greene's books. I forget what it was called. It's the one that you have, Sam, in your library.
Universe?
That's it, the Elegant Universe.
Yeah.
And according to you, if you're traveling at relativistic speeds or you are very deep into a gravitational well, time to you would feel like any other time.
That's right.
And so, you know, these biological processes, like, does your heart actually physically beat slower? No. Like, if you were just sitting in that well or traveling at a great speed, it would be like on a moving train. Like, you wouldn't experience anything physically different. It's just yeah.
That's right. Yeah, yeah. This is the absolutely mind-boggling aspect of the universe that Einstein revealed with his special theory of relativity, which actually preceded the general theory of relativity. And the amazing thing is exactly what Ryan just said. It doesn't matter how fast you're moving through space or the strength of the gravitational field that you're moving through. You experience the flow of time exactly the same as if you were motionless. Nothing changes for you. It's only the outside observer that is not traveling that fast or not in such a strong gravitational field that sees time slow down for you. And this is the truly strange thing about our universe. And it really all hinges on two fundamental ideas. And I was actually just giving a presentation about this to my astronomy class. So I might actually bring up the PowerPoint presentation that I just gave on Monday to my astronomy class, because I think it will help to fill in some gaps of what we're talking about here. Let me see if I can find it here. It was all about the speed of light and just how truly strange it is compared to everything else that we experience in the cosmos. I think it's coming up here. All right. So I'm just going to go down to this slide right here. I won't worry about the two before it. So the craziest thing, I think, about the nature of light, which is all electromagnetic radiation, whether it's radio waves or microwaves, visible light, infrared, et cetera, is that the speed of light is invariant. And what that means is it doesn't depend on any frame of reference. So here's a little example that I showed my class on Monday. So let's say you're standing on a runway. Okay, so here's you standing on a runway, and there's a fighter jet on that runway as well, not moving. And there's a little laser beam that's shooting out of the jet. And that laser beam is moving at the speed of light towards you. And if you made a measurement of that laser beam coming off that stationary jet on the runway, you would measure the speed of light at roughly 186,300 miles per second. That's the speed of light that we can calculate. Okay, so fine, no big deal. Okay, so now you stay on the runway. The fighter jet takes off, and it does a circle, a loop, and then passes you in the same direction that it was pointing at you before. This time the jet's moving at 1,500 miles an hour as it flies towards you. You're still standing still on the runway, and you still measure the exact same speed of light, even though that light beam attached to the jet is moving towards you at 1,500 miles an hour. Well, that's crazy, right? Any other time you would add up two relative velocities, the velocities would just add together, right? I think Ryan mentioned standing on a train earlier. So yeah, if you were standing on a train moving at, let's say, 50 miles an hour, and you threw a baseball in the same direction the train was moving at 50 miles an hour, then the baseball would have a velocity of 100 miles an hour relative to someone standing on the ground. No big deal. But light doesn't do that because its speed doesn't have any frame of reference. It's invariant to any frame of reference. It's always the speed of light in the vacuum of space. Speed changes if you're moving through an atmosphere or if it's going through water or some other substance. But in space, the speed of light is the speed of light, regardless of how fast that light source is moving towards you or away from you. And that's fundamentally different than what we experience in our everyday lives. And I've done some research onto why this is. And the short answer is we don't know. Nobody knows why the speed of light is invariant, but it's just a fundamental fact about this universe. And we just have to accept it and move on. But I think this is one of the biggest hurdles to wrap your brain around in understanding special relativity and general relativity as well. But the speed of light doesn't depend on any reference point.
Well, I think also we just want to comment on one more thing. When you brought up Galilean relativity, in which the velocities do add together, there is a little bit of a correction due to that Lorentz transformation. So when you're throwing a baseball at 50 miles an hour, it is going like a tiny bit faster, but like a billionth of a mile an hour, and we just can ignore that because it's so insignificant.
That's right. Yeah. So I love that you brought up like the transformations, right? So the transformation is just a way for us to take a measurement that we have, whether it be the velocity of something, and then move it into another frame of reference, right? So the analogy was the train, right? You're going 50 miles an hour on the train. You throw a baseball in the same direction, 50 miles an hour, and to transform those velocities to a stationary observer, we can use the Galilean transformations. Galileo figured out how to add velocities together 400 years ago. And his equations work perfectly if you're going at slow speeds, like 100 miles an hour, even 1,000 miles an hour, or even 100,000 miles an hour. The Galilean transformations work just fine. But they break down once you start getting close to the speed of light, and they no longer work. And that's because the speed of light is invariant. We don't understand why, but it's just one crazy fact about the universe that we have to assume. But there's an even crazier fact about the universe, which plays into our experience of time dilation. And this is the other monumental discovery that Einstein made just through pure thinking and some mathematics. So Einstein realized that time didn't just flow like we normally experienced it. He realized that time was actually another spatial dimension of the universe. And, you know, I don't know how to actually conceptualize this. I've seen the equations, so I get that part of it. But Einstein basically said, no. We don't live in the three-dimensional universe that we experience on our day-to-day life. We really do live in a four-dimensional universe, 3 dimensions of space and 1 dimension of time. And that truly is a totally different way of conceptualizing the universe. It's not space plus time. It's something totally new. It's space-time. And it's that continuum that leads to the effects of time dilation and other bizarre things when you travel really, really fast. But this is the other strange thing about the universe that we think we actually live in now that's hard to wrap your brain around. So Einstein gets this far, right? He realizes that the Lorentz transformations that Ryan mentioned, Lorentz was another physicist who figured out how to add velocities close to the speed of light. He corrected the Galilean transformations. So Einstein realized that the Lorentz transformations were correct. And it was because of the invariance of the speed of light from any reference frame. He realized that the continuum that we're moving through is space and time combined. Space is another, or time is another spatial dimension. And then he went a step even further. And this is the other big part that we just have to accept about the universe. We don't understand why it is. We just know that it is. And that's the cosmic speed limit of the universe. So Ryan, you mentioned causality earlier when we were talking about black holes. And there were some pieces that seem to violate causality. So when we talk about causality, we're talking about the extent to which one object can have an influence over another object, and the speed at which that causal relation can actually propagate from one object to the other. And it turns out that our universe actually does have a cosmic speed limit for causality. There's a maximum speed at which one event can cause an effect on another event. And not coincidentally, it's the speed of light. It's the speed of light because light, made up of photons, are massless particles. And so there's no impediment to their motion, right? So we call impediment to motion mass, or inertia, the amount of energy it takes to get something to move and keep it moving. But because photons are massless, then there's no impediment to their motion, so they can move at the fastest speed limit allowed by the universe, the cosmic speed limit, the speed of causality. And that's what Einstein realized on top of his other brilliant insights, that the speed of light really was a maximum speed limit for the universe. Not because light has anything to do with it, but because light is made up of massless particles called photons, and there's no impediment to their motion. So questions, comments about that before I delve into how that actually leads to time dilation?
If we know that light can be affected by certain forces, and forces are what cause accelerations, how does that not cause an acceleration of light?
So you're correct that light is affected by the gravitational force, right? So we know that light actually gets bent by the warping of space, just like mass does. And that's because the curvature of space really is gravity. So we can't really think about gravity as the same type of force as the electroweak force, or as magnetism or any of the other fundamental forces, because gravity really just is the warping of space-time itself. And because of that curvature, light follows the same curved path through curved space-time as mass does. So why or why not does that lead to light being accelerated? Is that what you were asking?
Yeah, I guess why not? But you said it's different, so it makes sense.
Yeah, I think like on a macroscopic scale, you can treat gravity as a legitimate force, but then when you're taking into account relativistic particles, particles traveling at relativistic speeds, I think it would be more useful to just treat gravity as, like Sam said, just a bending of space-time, and not like a real force that can provide acceleration.
Yeah. So here's the piece about the why the speed limit is the speed limit, because it really is about the geometry of space. It's actually the four-dimensional universe that we live in which dictates this causal speed limit, the maximum speed limit. And I'll explain it in this diagram here, and then you guys can ask any questions if you have. So here's a crazy thing. So the assumption that we have to make with a cosmic speed limit, which we know to be the case, and with the four dimensions of space-time, is that any object moving through space-time has to have a component of its velocity in time and a component of its velocity in the three spatial dimensions. So this little chart shows that. I've combined the three spatial dimensions along the x-axis, and I've put the time, which is another spatial dimension, along the y-axis. So this shows the four dimensions of space-time. So that's, I think, fairly straightforward. One dimension of spatial time, three dimensions of the space that we're normally familiar with: up, down, left, right, forwards, backwards, right? Three dimensions of space. Okay, so let's assume that we're not moving relative to wherever we are, right? So right now we're not moving relative to the chairs that we're sitting in, and we're not moving relative to the Earth. Okay, so we have no velocity in the three spatial dimensions relative to our current position. So all of our velocity then is in the time dimension. And so as we proceed through that dimension, which we're proceeding right now, we experience time at the fastest rate possible, right? Because our full component of all our velocity is along the y-axis. So the passage of time is as quick as possible because our motion is only through time, because we're not moving through space at all. That makes sense, right?
Mm-hmm.
More or less, as
Yeah.
crazy as it sounds. Okay, so now let's say that we start moving through space. So we start moving through space. Now we have a component of our total velocity in the spatial dimension and a part in time. So as we proceed along this path, our velocity through time is not as great. So that component goes down, and the experience of time for an outside observer watching us is that it slows down, because our full velocity is no longer in that spatial dimension. We're not moving as much in that spatial dimension. So take it to an extreme. Move through the 3 spatial dimensions faster and faster and faster, so you get almost only moving along the x-axis. And as you can see, your component of time approaches 0. And that's why time slows down as you move faster and faster through the 3 spatial dimensions.
I think I watched a YouTube video about this kind of thing, and the first assumption that he stated was like, everything moves at the speed of light. It's either through space or through time, or a combination of both.
Yeah, and that's the other amazing leap that Einstein made, that everything in the universe is moving through space-time at the speed of light. And once you start looking at the math, it's the only way to make sense of our observations of time dilation. The only way to make sense of the slowing of time relative to an outside observer is that if everything is actually moving through space-time, through this continuum at the speed of light always, and you can change those components by moving really quickly through the 3 spatial dimensions. That's a mind bend, right?
So if you're moving through space at the speed of light, then you're not moving through time at the speed of light. Therefore,
Light doesn't experience time.
yeah, exactly. However, everything else that is moving through time at the speed of light obviously goes through it much faster than you do. Hence why years can go by on Earth if you are moving at the speed of light somewhere else.
That's it.
Okay. Yeah. Wow.
Yeah. And there are some physicists that would argue that it's meaningless to talk about photons not experiencing time, because there really is a mathematical limit to approaching the speed of light. Nothing with mass can actually accelerate to the speed of light. And that seems to really be true in the universe we live in. And so when you talk about something traveling at the speed of light, a photon, time really doesn't have any meaning, nor does space. So a photon doesn't actually travel through the universe. It's instantaneous. So to a photon, there's only been a moment since the Big Bang. It hasn't, experienced the 13.84 billion year history of the universe, nor has it experienced moving through space at all. There's no distance that something traveling at light speed experiences. So some physicists would say it's meaningless to talk about photons experiencing no time, because they don't experience space either. But your point, Dave, is correct to conceptualize this. Time does seem to stop for an object, a massless object traveling at the speed of light, or come very close to stopping for subatomic particles that we can accelerate to 99.99999% the speed of light, like in the particle accelerators in CERN.
Why can't we get them to that speed?
To the speed of light?
Yeah.
Yeah, I mean, this is one of the philosophical questions. We don't know why the universe has a cosmic speed limit. We know that it does, and we know to accelerate an object to that speed, it would require an infinite amount of energy. Yeah, when you look at the equations of general relativity, it becomes clear that as an object gets closer and closer to the speed of light, the energy required to further accelerate it closer to the speed of light it requires an exponential increase in the amount of energy. And as you approach the limit of the speed of light, the amount of energy needed to further accelerate it becomes infinite. but we're talking at like 99.109s,
Yeah.
close to the speed of light. That's when the amount of energy would become close to infinite.
That's just strange.
Yeah, it's super strange. And like I say, we don't know why the universe has a causal speed limit, but it does, and we don't know why it is the magnitude that it is. It just has to do with the other fundamental forces and quantities that we find in the universe: the mass density ratio, the strength of an electron, et cetera, et cetera. They're all these fundamental constants that dictate the way this universe works. There's no reason to believe that it's the same in other universes if other universes turn out to exist. But in our universe, these are the rules of the game. So that's time dilation, Dave. It's all about these bizarre fundamental aspects of the universe, the invariance of the speed of light and the cosmic speed limit, the speed of causality, and the fact that according to general and special relativity, everything in the universe moves through space-time at the speed of light. And then when we modify our velocity through space, the time component drops. And time seems to slow down for an outside observer. Not for the person actually moving at that speed. Time stays the same for them. But to an outside observer, time seems to slow down.
There's a lot more to go with when I get that question again then. Sweet.
Yeah, you can show them the slideshow next time. Have it handy on your smartphone.
Yeah.
So that was kind of a deep dive into special relativity. General relativity is really an offshoot of special relativity. Einstein realized that there needed to be a more expansive explanation of how things move through the universe. And the theory of general relativity did just that. He applied, these fundamental things about the speed of light and the four dimensions of space-time into a new formalization of gravity, being just the curvature of space-time itself. And every test that we've ever done in the last 100 years has confirmed Einstein's predictions to greater and greater degrees of precision. I think we're out to like 20 decimal point places right now of precision in confirming Einstein's theories. So if he's wrong, he's not wrong by much. It's a really, really small amount. And you can really sum up all of general relativity in 2 sentences. And I think it was Archibald Wheeler who came up with this statement, but I could be wrong about that. I'll have to figure out who said this. But the 2 sentences that sum up general relativity are: space tells mass how to move, and mass tells space how to bend. And I should have used the term space-time to be accurate. So space-time tells mass how to move, and mass tells space-time how to bend. So there's this really beautiful interrelationship between space-time and mass that cause the curvature of space-time and dictate the way mass moves through space-time. And I love the fact that the two have to interact in that way for gravity to be. I think that's pretty cool. And that's another way that it's distinguished from the other forces. There seem to be these like force carrying particles. So you could say that there is a relationship between the way these force carrying particles interact with the force fields of the various forces. You could say that's similar to the way that mass and space-time interact. It does seem to be a little bit different. So that's time dilation, general relativity, and special relativity in a few minutes.
We're going to derive the Ricci tensor.
What's that?
We're going to derive the Ricci tensor.
I'm not going to do that right now. If you'd like to, you are welcome to. But really, it was all of these stunning observations of the universe that led to the prediction of black holes. Black holes really are one of the predictions that came out of the special and general theories of relativity. And it came from people thinking about the extreme cases of what it would mean to have curved space-time. And let me bring up an interesting diagram for us to see here. So when Einstein and his colleague Rosen were starting to think about the idea of black holes, there was a corollary theory as part of that, which were called white holes. Why do I keep going to these weird links? Anyways, we'll just use this image right here. And so when they were figuring this out mathematically, they realized that, okay, so this black hole is a region in space where the escape velocity would be greater than the speed of light. Anything that passed the event horizon couldn't escape. There's probably an opposite to that called a white hole, which would be a region in space where nothing could enter into. It would only be a region where radiation and matter would come out of. And between those two would be a bridge, which became known as an Einstein-Rosen bridge, and later as wormholes. So that's really the birth of the conceptualization of wormholes from the original work of Einstein and Rosen. We don't know if they're real or not, but you know, theoretically they're possible. This is not what Roger Penrose and the other two physicists got the Nobel Prize for, but they remain, I think, some of the more tantalizing parts of theoretical physics that you know, are portrayed in science fiction movies pretty often. What do you guys think about wormholes?
I think it'd be interesting if we found one.
Yeah.
I wonder what we would do with it, where we'd end up. I wonder, like, if there's a limit to how far away you can portal out of it. Like, can it bring you to the opposite side of the universe?
Yeah, I'm not sure that there are limits in and how you know, how long Einstein-Rosen bridges can be. I'm not sure.
I think it would also have influence on cosmology, just like the geometry of the universe, whether it has positive or negative curvature, and like the overall structure, like what the shape of the observable universe is, if it's a sphere or a salad or flat.
Yeah. So, I mean, it's interesting, right? So there are a couple fundamental problems with traveling through wormholes, especially through Einstein-Rosen bridges. One of them is that the wormhole might actually pinch down to a singularity in its center. And if that's really true, then there's probably nothing that can travel through it. So if it does pinch down to a singularity, it's not going to be a possible way of actually moving from one place to the universe to another. The other fundamental problem with wormholes that Stephen Hawking really took issue with is that you not only would come out at a different space in the universe, you could also potentially come out at a different time, potentially in the past, potentially in the future. But if you came out into the past, it could actually cause time paradoxes. You could show up in the same place that you went in, but 100 years earlier, and inadvertently change history so your grandfather never met your grandmother. And so you wouldn't be born. And so Stephen Hawking said that that type of time travel through wormholes, or time travel in general, was impossible because the universe wouldn't allow those types of time paradoxes. What do you guys think about that?
Stephen Hawking was wrong plenty of times.
I think Stephen Hawking was wrong.
Plenty of other times, you know. Maybe this time.
I was wondering, how could a wormhole bring you back to another time?
Yeah, so I mean, it's a portal not just through space, but through space-time. We don't really know what happens when you move through a wormhole. There are really three possibilities. You go in one side of a wormhole, and you come out to the other end of the wormhole at a later time than when you went in. There's a second possibility that travel through a wormhole is instantaneous. So you come out the other end of the wormhole at exactly the same moment that you went in. And the third possibility is that it takes you to a different space-time where you actually come out of the other end of the wormhole before you went in the first end.
I like that one.
But I feel like the only way to do that would be you'd be in a different region of space. And then the only way to get back to your original position would be to travel through time so that you would never have a paradox.
What do you mean? Say more.
I think, well, yeah, I'm still struggling to understand how you can return, like on the other end, return to where you were at an earlier time.
He thinks that
I don't think you can return. I don't think you can get back through the same wormhole, right? Because you'd be on the white hole side. There's no way to get in the white hole. So you'd have to have another flipped Einstein-Rosen bridge to get back.
Yeah. So then how could you create like a grandfather paradox?
because you could like I don't know, the butterfly effect. Destroy something.
No, that's totally what it, yeah, you could go back and like fall in love with your grandmother.
Mm-hmm.
Right? So then do you exist in the future if your grandmother and grandfather never actually had kids?
Well, of course, but then
Maybe you were always your grandfather.
Yeah, you get old and realize
It was you the whole time.
but you would have to return, like going through the black hole, you would have to pop out the other side somewhere relatively nearby so that you could have an influence on, let's say, your grandparents.
That's right. There's no reason to believe that the wormhole would actually take you to a different space in the universe. It might just bring you back to a different time. Remember, like time is just another spatial dimension in space-time. There's no guarantee that the wormhole brings you to a different part of the universe in space. It just might be a different part of the universe in time.
Yes.
Okay, I'm still struggling with that. I don't think that.
I mean, it's like the brain can't actually conceptualize time as a spatial dimension, right? We're too accustomed to like time as like flowing from the past to the present to the future. But Einstein said that is not the case. Einstein said that time is just a physical continuum, that all time is actually already here, right in front of us in every direction.
Mm-hmm.
We're not moving through time from past, present, and future. Any point on the space-time continuum is just that. It's just a point on the space-time continuum. All time exists in every moment, and you can move through it through a wormhole.
All right.
Yeah, there are some really cool, I think they're called Minkowski diagrams. The one that I showed in my PowerPoint is a really simplified Minkowski diagram. Minkowski was Einstein's mentor and helped Einstein out with the math, actually, with special theory of relativity and general theory of relativity. But you can see these space-time diagrams which demonstrate that literally, like the existence of anything can be demonstrated as a line on the space-time continuum. And it can't be said to exist in a certain specific time, past, present, or future, but in space-time. So when you make that leap and start conceptualizing time as a spatial dimension, the whole concepts of like past, present, and future, they don't exist in the way that we normally think about them. Time just is, just like up and down are, or left and right is, back and forth are, right? We wouldn't say that like behind us is the past. No, behind us is like always there. We can turn around, we can see behind us. It's not that it's over. And Einstein said the same is true with time. It's a physical dimension that extends in a continuum. So time just is, just like the other spatial dimensions.
Okay, here's what I would like to try to conceptualize intuitively.
Yeah.
A wormhole, let's say, existed right next to us.
Okay.
And I just want to travel through time because it's a fabric back to the Wyoming Stargazing Office in 2015.
Okay.
How can that be possible?
I mean,
intuitively, I want to like have an explanation for that.
yeah. So that wormhole only moves through the time spatial dimension. It doesn't move through the 3 dimensions of space. I mean, so the fabric of space-time, the space-time continuum, doesn't separate time and space. And so we don't know when or where the wormholes actually connect to. It could be a when and a where. It could be a where, or it could be just a when. And nothing's violated with the way space-time works.
Well, here's the thing that I can accept, and here's the thing I can't accept.
Yeah.
The thing I can accept is taking a wormhole, let's say, right to Andromeda as we see it right now. And so
Sure.
then you're teleported, let's say, 2.5 million years into the past.
Okay.
And then no paradox can occur because you cannot influence anything that happened back here on Earth, because you need to travel, like, let's say, faster than the speed of light, which is impossible.
Right.
But what I can't understand is how you just travel back in time at the present space. So like in this office 5 years ago.
Yeah.
Because then
Yeah,
you would
so-
have paradoxes.
Yeah, it's crazy stuff. I would suggest taking a look at these Minkowski diagrams. So the Minkowski, let me bring up a, hold on. Let's see. I think they're called, so
Right.
here's a really simple like Minkowski diagram that shows like the past and future light cones. And so these lines right here represent travel at the speed of light. This line right here and this line right here. So there's a region of space-time that is permissible within the confines of our universe, that a past event can actually have an influence on a future event. So there has to be some kind of communication or causal influence traveling at or less than the speed of light. So these areas of the diagram represent that. Events within the past light cone and events within the future light cone. Well, traveling through a wormhole, you're not really traveling through space-time anymore. It's a rip or tunnel through space-time. Space-time's around you, but you're not traveling through it. And so you could potentially violate the type of limits of travel through space-time represented by this diagram. You could potentially be out here or out here in the past, in the future, because you're no longer traveling through space-time when you're moving through a wormhole. And that's why you can end up in the past or the future, because you're no longer in this area of space-time dictated by less than light speed travel for a massive particle.
Okay. Yeah,
I know
would say,
it's like it's a total mind bend, but my understanding is that's the deal. Wormholes allow you to get out of this this past and future light cone.
I see. Perhaps there's maybe just a limit to how far away or how nearby you can go if you were to time travel. And you can sort of think of another thing, like if beings existed in Andromeda, according to them, we don't exist yet.
That's right.
Like, it's still, you know, humans don't exist yet.
That's right.
To that. So it's
yeah,
like,
I mean,
yeah, we're already living in the past.
I think Australopithecus exists if there's any telescope powerful enough in any planet on Andromeda that's looking at the Earth. All they're seeing is like Lucy walking around on the surface.
Yeah.
About 2 million years ago, which is kind of a cool time frame to talk about with people who are learning about distances for the first time.
Yeah.
But that's not time dilation. That's just distance and the fundamental limit to the speed of electromagnetic radiation. If the speed of light was instantaneous, infinite, then that wouldn't be an issue at all. We'd see the whole universe as it is right now. But that's not the case. It's got this finite speed, so we can only see the universe in the past. Well, that was fun. So thank you, Roger Penrose, and Reinhard Genzel, and Andrea Ghez for your work on supermassive black holes and smaller black holes. We definitely still have a long way to go to understanding how black holes work. Maybe next time we can talk about Hawking radiation. That's truly one of the most bizarre parts of black holes, or maybe relativistic jets. That's another interesting one as well. But long and the short of it is that there are lots of stellar mass black holes that are 5, 10, 20, 30 times the mass of our sun. And then there are these supermassive black holes, which exist in the center of most galaxies in the universe, if not all of them. Interestingly enough, we've never found an intermediate black hole, an intermediate mass black hole. So there's still kind of a big gaping lack of understanding there. And maybe that'll be the next discovery that we talk about on Astro-BS. You never know. Any closing thoughts or ideas, guys?
Well, it would be a real bummer if we found out that wormholes exist and they function the exact way we've always talked about, but then we find out that there's a singularity of the middle.
That would be disappointing. Anything else?
I hope that doesn't happen. But that's about it for me.
Matt, any words of wisdom?
Keep doing some research.
I was trying to think of another food analogy, but I got nothing at this point.
Oh yeah.
Join us next time for Astro-BS for Matt to share his latest and greatest food analogies to the cosmos. Thanks for joining us this week, and thank you guys. Appreciate your time, and we'll see you next time on Astro-BS.
All right.
See you later.
Sounds good.
See ya.
I know.